Welcome to today's SaferSim webinar. I'm Jacob Hayden, and I am a coordinator for the SaferSim University Transportation Center. The SaferSim webinar series features researchers and students sharing detailed information about their projects. These projects usually use simulation to address transportation safety issues. Thank you for joining us today. Before we get started, I do want to point out the chat box in the lower right-hand window of Adobe Connect. Please use this chat box for any questions or comments. There will also be time at the end of the presentation for these questions and discussion. So now I'm pleased to welcome our presenters from the University of Puerto Rico Mayagüez, Dr. Didier Valdes and Dr. Benjamin Colucci.
Good afternoon to all the participants on the SaferSim webinar series today and in the previous webinars.
Well, we will start our presentation titled Operational and Safety-Based Analysis of Varied Toll Lane Configurations as part of this webinar series of SaferSim. We will be presenting the research that we are performing at the University of Puerto Rico at Mayagüez. I will let you with Dr. Colucci.
Good afternoon. First of all, we want to acknowledge that this is a project for the U.S. Department of Transportation. Dr. Valdes and myself are the principal investigators. And the research that we're presenting this afternoon is a combination of two studies that were conducted by two of our master students, Brian Ruiz. He just completed his Master of Science in Civil Engineering from the University of Puerto Rico at Mayagüez. And he's also the 2018 National and International Avertis Award in the Master's category. His special, his research study was associated with signage and pavement marking in a dynamic toll lane at the PR-22 in Puerto Rico. The second study that we're presenting was conducted by Jonathan Ruiz, who was also a recipient of a Master of Science in Civil Engineering at UPRM. He's also a 2000 Avertis Award, but on the highway safety category. And his research topic is associated with roadway geometrics and specifically the effects of posted speed limits and lane widths on driver behavior in the same dynamic toll lane. The general outline of the webinar is presented in 5 parts. We have the general introduction, the objectives of the big project and the 2 special studies, a brief overview of the UPRM driving simulator, and we will enter specifically on the details on the dynamic toll lane simulation studies, the roadway geometric and posted speed limit conducted by Jonathan, and the signage and pavement marking conducted by Brian, and then we will merge the conclusions and recommendations of both studies. In terms of introduction, worldwide, there's definitely an issue on traffic congestion and major delays in most of the most important metropolitan regions where transportation infrastructure has not kept essentially with the increase in vehicle demand. This has been documented by several agencies, specifically the Federal Highway Administration of the US DOT. Certainly, the congestions and associated delays has a negative effect not only on the environment but also on the social and economic development of urban regions, and that has been documented by Federal Highway and other authors. In terms of roadway geometrics, what is pertinent is in terms of acceleration and deceleration lanes, entrance and exit gates, and gore areas. And those areas where we have a pattern, a speed differential is where it's more of a safety concern for road users. In terms of the posted speed limit, in this particular case that we're evaluating, the DTL, is the perceived inadequate posted speed limit that is in the order of 45 miles an hour in both directions, and in one segment is reduced to 40 miles an hour. The perception is that affects the driver's expectancy. Furthermore, inadequate signage and pavement markings following the requirements of the Manual on Uniform Traffic Control Devices, it is our opinion that increases variability in driving behavior. All these inconsistencies, all these design inconsistencies affect both operational and safety performance of existing toll facilities. To provide the adequate perspective to these two studies, let's just bring some definitions on board. Let's start with managed lanes. In the context of this research project, these are highway facilities or a set of lanes in terms of their operational strategies are implemented and managed in response to real-time conditions. This has been very well documented by several studies, and an example of them are shown here. Fitzpatrick, Federal Highway, and Gooding have documented those effects of managed lanes in real-time conditions. But what is pertinent is that provides an alternate road both inbound and outbound to the San Juan metropolitan area. That's where we conducted the study. In terms of operational strategies, there's issues associated with pricing, congestion pricing, variable fare, depending on what time of the day is the peak hour, and also in terms of the type of access control, and in vehicle eligibility and sharing of what vehicles can use the facility. In our case, we have a shared facility that has private vehicles and also the BRT, a bus rapid transit, heavy trucks that have more than 11,000 pounds are not accepted to use this facility. In terms of an overview of the corridor, we have to start first with the PR-22. It's a corridor that goes on the northern part of Puerto Rico, goes from San Juan to the west, going to Atillo and another town named Arecibo. That particular corridor is 52 miles in length, or 84 kilometers, and it has roughly an average annual daily traffic of close to 110,000 vehicles per day, almost 111,000 vehicles per day. In terms of its pertinence, because it's the first reversible dynamic toll lane in Puerto Rico, and it's also on the new legislation on public-private partnership was also incorporated. There's a cross section of the PR-22, as you can see. You have in the middle, you can see the 1 meter barriers where the traffic that uses the DTL is confined. And as I mentioned, we're on the share mode that you have on the dynamic toll lane. You can provide vehicles on the BRT, and on the main line you have lanes that are 3.65 meters or 12 meters wide, with a 3 meter shoulder on both sides. Now let's get on the details of the DTL. The DTL by itself, the ones that was evaluated in this project, is a segment of 6.4 miles in length, or 10.4 kilometers. There was an extension later on 2.2 kilometers that was out of the scope of this research. That facility right now, in terms of penetration, takes about 6% of the total traffic of the PR-22, with an IDT almost 6,200 vehicles per day. And as I mentioned before, it's shared by by both private vehicles and BRT. And 2 lanes that are reversible, 12 feet wide, and the concrete barriers that I mentioned before. Okay. It also has a small segment, has a pocket shoulder lane, but it's going to be shown later on its effects. Posted speed limit 45 miles an hour eastbound and westbound, and there's a reduction of 40 miles an hour in the exit toward Toa Baja. Those are the 3 operational strategies that we mentioned before. And in terms of traffic schedules, starts in the morning around 5 o'clock in the morning until 11 a.m., headed eastbound towards Bayamon, and in the afternoon and nighttime, it starts at 1 p.m. through 9 p.m., and also on holidays. What are the potential safety issues that we encounter in the DTL? But essentially, there's 2 that we pay close attention in our research. The speeding behavior through the DTL at the posted speed limits that we mentioned, 45 miles an hour and 40 miles an hour on one exit, and the incorrect maneuvers primarily on the exits of both eastbound and westbound. In terms of speeding behavior, we show the 6 locations that we analyze: the DTL entrance eastbound, DTL exit eastbound, as well as the DTL entrance westbound and the exit westbound. And we have a bridge pier more or less halfway on the corridor that the traffic speed, there's like a split on both sides, and it's before the bridge pier separation and after bridge pier separation. And as you can see, in all the 6 categories, the average running speed is higher than the posted speed limit of 45 miles an hour, with an increase of almost 18% at the DTL exit with 54.8 miles an hour, and before and after the bridge piers, 18 to 19% increase in the average running speed as compared to the posted speed limit. We're showing the incorrect maneuvers. Here we're presenting the DTL, the detail on the exit, and something to keep in mind is that in the United States, according to the ASH Topology and Geometric Design policy for streets and highways, most of the driver expectancy is that the exit will be on the right-hand side. In our case, the exit on the right-hand side is the BRT, the Bus Rapid Transit, and the drivers, even though there's some signage ahead of time, saying that what is the lane to take, most of the maneuvers are that many of the drivers go to the right-hand side without following the message of the sign, instead of taking the express lane that is on the left-hand side. Okay. We have a table on the right-hand side that you can see the direction westbound and the traffic in terms of vehicles per day, 3,575 vehicles per day, and how many wrong maneuvers on a day. Taking the wrong exit was 22, and other vehicles, when they noticed that they're taking the wrong exit, they went on a reverse maneuver. There were some of the cases shown the westbound, and twice on the westbound it happens. Okay. Our research objectives are to develop a representative driving simulation scenarios for the existing condition, we call configuration 1, and develop scenarios for the proposed conditions, we call that configuration number 2, using signs and pavement markings based on the design manuals and supplements. The design manuals specifically is the manual on uniform traffic control devices, the revised version of May 2012. And the supplements are the Spanish manuals in Puerto Rico for signage developed by the Department of Transportation and Public Works of Puerto Rico. Other research objectives include the evaluation and comparison of driving behavior of the subject drivers that are exposed to the existing configuration and to the proposed considerations when they are approaching the PR-22 dynamic toll lane exits. And we will finish with conclusions and recommendations based on these results to see how we can improve the operation and safety of the DTL, and what are the short, medium, and long-range recommendations. Okay, let's go to the study number 1. In that one, we will consider which lane width and posted limit presents the least variability in terms of driving behavior. And we have 3 independent variables: operating speed, acceleration, noise, and lateral position. And then we're going to compare and validate the results with a linear model and a non-linear model. The second study, we will concentrate on signage and pavement marking combination. Again, signage and pavement marking combination that presents least variability in driving behavior in terms of those 3 independent variables: lateral position, operating speed, and acceleration noise. The UPRM driving simulator was the one used for both studies. This uses the software by Real-Time Technologies, and essentially the 3 main components, and many of you have seen in other simulators. We have in our case, it's a driving cockpit, and we have a visual display 110 degrees on a computer system that on this system that we use, And our cockpit is portable that we can bring to other locations that we want to give presentations outside our laboratory. In the screen, you can see on the left-hand side the UPRM simulation that we have done. We're already inside the DTL. You can see on the right-hand side the original system. We're approaching the bridge that we mentioned, and you can see the signage in Spanish. It's saying exclusive lane 2 kilometers on the right-hand side with a regulatory sign and with a warning sign below. Then we're getting out of that particular section. That's one of the zones of interest. Zones of interest are DTL entrance and exit and the bridge, and then it's repeating back again. Let's enter now in details on the study number 1 on roadway geometric and posted speed limit. In terms of hypotheses, the subject drivers with narrow lane simulations will have lower operational speed and lower acceleration noise, but higher variance in lateral position than those exposed to the scenarios with wider lanes. Our second hypothesis, subject drivers will tend to have a higher speed profile than the posted speed limit. And the subject drivers on average will use incorrect exit gates. Merging or diverging segments will present higher variability. The experimental design was a full factorial 3 to the k design with 27 scenarios. 3 independent variables: the time of the day condition, both morning, afternoon, and night. Lane width was 10, 11, and 12 feet, and the posted speed limit 45, 55, and 65. 3 dependent variables: operating speed in miles per hour, acceleration noise miles per hour per second, and lateral position in feet. We have 54 participants, and each of the participants run 3 of the scenarios. These are the zones of interest. We have 7 of them. DTL entrance, pocket lane in the left lane. That repeats as number 6 and 7, pocket lane in the right lane, and DTL exit because it's a reversible lane. And the separation prior to the overpass bridge columns, again in both directions. And the length of each one of those zones of interest is shown on the right-hand side. The longest length was the DTL entrance, and the shorter ones are the ones prior to the overpass bridge columns and after the overpass bridge columns. These are some of the statistics in terms of gender, age group, and gender. You can see that there's a reasonable distribution of males and females. We had 56% males, 44% females. And the age group were 3 age groups: 18 to 25, 26 to 45, and 46 to 70. And you can see a reasonable distribution on the 3 groups. We also, in terms of validation procedure, conducted a t-test at 95% confidence. And essentially, you can see that there were 3 zones that do not have a statistical significant difference. Those are the prior to the bridge separation and at both the exit on eastbound as well as westbound. And you can see the results of the real world, the mean speed, and the driving simulating operating speed, that there was essentially no significant difference. As you can see, the p-values 0.233 to the prior to the bridge separation, and 0.244 to the exit eastbound correction, and 0.09 to the exit westbound. In terms of operation speed analysis, you can see the general linear model on the left-hand side, and that particular one, you can see that the 3 independent variables. In this particular case, is for operating speed in zone number 4. That's at the bridge segment. You can see time of the day condition on the left, lane width on the right, and posted speed limit. Lane width on the middle and posted speed limit on the right. And you can see on the bottom the variables is morning eastbound, afternoon westbound, and nighttime westbound. These are repeated for each of the zone of interest. And on the right hand side, you can see the random forest model. In summary, the operating speed, you can see that in terms of the morning eastbound going towards San Juan metropolitan area, where people are going to work, is where you have the highest operating speed with 58.33 with respect to 45 miles an hour. That's over 24% increase in speed. In terms of the afternoon westbound, you can see a little bit less, 56.55, and nighttime 56.61. There was no significant difference on those 2. In terms of lane width, at 10 feet, there's a narrow width. The speed was almost 60 miles an hour, and that was to our surprise. And 11 and 12 feet that are wider lanes, they had a reduction in speed. In terms of the comparison of posted speed limit with operating speed limit, at 45 miles an hour, that was the posted speed limit. They were going almost 49.3 miles an hour. When it was posted 55 miles an hour, the subject driver went to an operating speed of 57.3, and when it was 65 miles an hour, essentially it was more or less the same, 64.85. That is also repeated for zone 7. For the sake we're showing only 2 zones. You can see that the same pattern is shown on both sides. But let me show more now on the right-hand side. On the right-hand side, we have the random forest model, which is showing the operating speed importance by independent variable in zone number 7, that is the DTL exit. And on the x-axis is the percent increase in mean square error. And they're already in order. Then you have the different variables on the left-hand side, and you can see that one on the top, that is the posted speed limit, that's the abbreviation, is the one that has the highest increment in mean square error with 23.9%. In terms of operating speed results, the operating speed dependent variable showed a statistical significant difference in all the 7 zones evaluated, and the highest increment in mean square error in 6 out of 7 zones, according to the random forest, was the posted speed limit variable. And this variable by itself is also the most important variable to determine the operating speed of the drivers. In terms of acceleration noise analysis, it's the same analysis as presented before. And again, you can see the difference of the results. Lane width, in this particular case, acceleration noise in zone 7, the dynamic toll lane exit, you can see that in this case, the lane width is the one that has the highest percentage increase in mean square error with 9.7%. In terms of a summary of those results, you can see the lane width variable for the 3 lane widths was statistically significant in 6 out of the 7 zones evaluated. The random forest model showed that the lane width independent variable was the most important in 3 out of 7, and the endpoint or access points associated with high crash frequency in managed lanes presented the highest increase in deviation of the acceleration noise with 2.07 miles per hour per second. Last, lateral position analysis. Here we decided to show you on the left the trajectories of the vehicles that participated on this study, and the random forest on the right. You can see that where's the bridge in the middle, where you see the elliptical part is where we have the bridge, and the lines are showing the first curve are the eastbound, the middle ones are the westbound, and the last one is also the westbound. But you can see that on the exits, particularly in the last one, you can see that there's the problems that they have incorrect maneuvers, and you can see people changing from one lane on the other in the middle as well. In terms of the random forest model lateral position in zone number 2, that is the pocket lane, you can see the distribution of the variables as well, and the summary of them are shown here in zone 7. 22% of the scenarios evaluated, 39% in the eastbound direction, that is the morning direction. The subject driver used the incorrect exit. Here we presented the table of the variables divided by time of day and lane width, and the 39% you can see that is on the first column on the morning eastbound that shows the 39. Other numbers are shown as well, and that shows you the 39%. The same random forest for the independent variable in zone 7. Here you can see specifically the same approach for eastbound, westbound, and westbound. But check on the middle one, you can see that during the afternoon condition, there was a scenarios 10 through 18. You can see the maneuver error, or the vehicles that will turn to the right. To the right was going toward the BRT, and you can see different trajectories that are the line is it's not as dense, showing the incorrect maneuvers on the left. And again, the increase in lateral position on the right hand side. And it shows again that the time of day condition results significant in 5 out of 7 zones evaluated. The time of day condition was between the two most variables in the random forest in 7 out of 7 zones evaluated. And the direction, eastbound versus westbound, as well as the condition of the day, morning, afternoon, or nighttime, affects the positioning of the drivers inside the DTL. In terms of the conclusions of this first study, it rejected the first hypothesis was rejected. Since narrow lanes, particularly 10 or 11 feet wide, present a higher operating speed and higher lateral position than the wider lanes, that is 12 feet. And the second hypothesis is accepted since the operating speed was higher on all the posted speed limit, a scenario of 45 miles an hour, in 6 out of 7 posted speed limit scenario for 55 miles an hour, and 4 out of 7. I'm giving now to Didier so he can continue. This will be the last one I'm presenting. The proposed optimum speed limit of 60 miles an hour inside the DTL and 55 miles an hour in the exit area shows less variabilities according to the random forest model. And the proposed lane width range to operate the BRT is between 10.5 and 11.5. And both random forest and general linear models show similar results and trends associated with the three dependent variables. Short, medium, and long-term recommendations. We are going to present these to Metropistas to see if they can increase the 45 miles per hour to limit to 60 miles an hour inside the DTL and 55 miles an hour in the exit gates. And then if they can consider implementing this proposed speed limit in the DTL facilities with adequate educational campaigns. And long-term will be an on-site study to evaluate the effectiveness of the proposed speed limits, and including the new extended 2-kilometer segment. In terms of geometric recommendations, we recommend to implement the optimal lane width with the corresponding pavement marking inside the DTL facility on the medium term, and again, long-term, conduct an on-time study. I'm giving now to Dr. Valdes, who will continue to the second segment.
Yeah, the second study is the signage, is related to signage and pavement markings. In this case, we were looking at the signage, the eastbound signage towards San Juan and the westbound signage. And there is a lack of uniformity in the signage that is very important and could influence driving behavior. And we would like to test if the combination of enhanced pavement markings and the uniformity improve safety and operations in the DTL. And here I'm just showing you 1 kilometer before the exit in the eastbound and westbound directions. And the signage is related to both of them was the one that I showed before, and it's different in both approaches, mainly because in one case the exit is to the left and the other case the exit is to the right. Here for the vehicles. Here I'm just reminding our audience about the problem with confusion when the drivers approach the DTL exit lane in the westbound direction. And in this case, we notice in the real world, and we notice also in our simulator, that people get confused and take the wrong exit. In the real world, they may even perform a reverse maneuver and trying to incorporate in the right exit, and that causes, of course, a lot of concern in terms of safety. So our hypotheses are, number one, that the subject drivers that use the incorrect lane when approaching the DTL exit will be higher in the base condition in configuration 1 and than the alternative condition that we will going to explore, and we will have different designs for that. And then the second hypothesis would be that the subject drivers will have less variability in our performance measures, lane position, speed, acceleration, noise, when traveling through the scenarios related to the proposed configuration. So in order to do that, we did this study in two phases. In phase one, we developed the scenarios with a proposed condition following the MUTCD. We went to the MUTCD, looked at the signs that were available, and we used them in order to test if changing the existing condition to something that was not different in each one of the exits, but similar, then the subjects will behave better. So in order to do that in phase one, we have the 6 representative scenarios and 2 configurations, the existing and proposed condition, and for independent variables, time of day and traffic flow for the morning, afternoon, and night time without traffic flow or with low traffic flow. And the analysis performed included several zones very close to each one of the exits and a multi-factor ANOVA and looking at the performance measures in those zones. So as you can see in this slide, the exit signage configuration in phase one, to the left, you have the existing condition, configuration 1, to the right, the proposed treatment. So as you can see, we're using here the HOV sign that is available in the MUTCD to stress the fact that this is only a lane where it says carril exclusivo. It means only for buses, and these signs corresponds to 1 kilometer before the exit and right at the exit. Now, in terms of pavement markings, we also proposed an intervention in configuration 1, the existing condition without any particular sign markings, and in the configuration 2 with the markings representing the bus and only bus and also the route shield for the freeway 22. Okay, let me tell you a little bit about our subject drivers for phase one. I'm going to accelerate a little bit now. We have 24 subjects, males and females, and 67% of participants knew about the DTL, the dynamic toll lane, and 33% had it as the facility at least once. So in terms of average lane positions for results for phase one, we really find some differences in the main factors, but without differences in the interactions between the main factors. But the situation is that, as you can see in these two particular figures, I'm showing here the lateral position of the vehicles, like a top view with the 2 lanes for each one of the scenarios, in configuration 1 in the top and configuration 2 in the bottom for each one of the cases that we are presenting, scenario 1 and scenario 2. And you can see that even with our signage for this phase 1, still some drivers took the wrong exit. Now in scenarios 3 and 4, there wasn't the case, and in scenarios 5 and 6, still 8% of the participants used the wrong exit, the BRT exit. In terms of average speed, there were no significant differences with the main factors or the interactions. In terms of the acceleration noise, there was some significant differences with some factors, but they were not very conclusive. So we identified that even using the MUTCD and the signs that were available, still there was some confusion. And I'm going to show you a little bit what we did, and part of the confusion exactly because of the understanding of the MUTCD signs. So we did a phase 2. In this phase 2, you can see in the little box there, the phase 1, analyze the results of phase 1, and then we did an online survey in order to let the drivers tell us what configuration they understood better. And then we developed the new scenarios using those results from the survey and did the rest of the study with the simulator. So the online survey, after the instructions, it had 6 sections with the demographic, the driving history, etc. And I'm going to show you the results, the main results here. Demographic information, mostly similar composition in terms of males and females, and between the ages of 18 and 54 years old. And you can see there the age distribution. In terms of the driving history, all of them were drivers, licensed, 87% obtained their driver license very early, etc. And in terms of understanding the MUTCD symbols, this is one of our main and major eye openings, because 65% did not understand the HOV symbol. And that was crucial, because this is something that we used in our previous experiment as an alternative to the current situation. So therefore, we decided not to use it anymore. But we found that the other 2 symbols were very well understood. So in terms of the section 4, selection of overhead signs for the express lane exit, we made some combinations in terms of the towns that that the people could reach from that point on, and the one that was selected by 63% of the participants in our survey was alternative E. And in terms of the overhead signs for the exclusive lane exit, the regulatory sign, then we also did the same. Here we have 3 signs actually that were very well understood. So we decided to, and now in terms of the selection of pavement marking treatments, also there was a very good indication that the combination of words and symbols was something that we should use in terms of pavement markings. So with these major findings, we started the design for the alternative condition or the proposed treatment. And now I'm showing you the proposed treatment configuration 2 in the right-hand side of this slide. You see in the westbound direction toward San Juan and in the westbound direction toward Arecibo. So, and in terms of pavement markings, we also use the proposed condition, the combination of words and symbols, only both, and the route shield symbol. Now I'm showing here subject drivers, and also for the phase 2, the average age, standard deviation. These are the statistics for the participants, and very quickly the average lane position results for this phase 2 with the new configuration. Now we found significant differences with more factors, and a significant difference also with the interactions between factors and the trajectories. Now you can see here very clearly that in both scenarios, scenario 2, 2 graphics at the left, and scenario 1 and scenario 2, 2 graphics to the right, you can see that in the upper part of that graphic, several subjects used the BRT exit, the wrong exit, 33% of the subjects. Meanwhile, in the proposed configuration, which is configuration 2 in the bottom figure, none of them use it. All of them were aligned already to the correct exit. Similar situation in scenario 2 in the figures to the right. Similar situation in scenarios 3 and 4, where the vehicles were already aligned in the correct path, in the correct lane, and scenarios 5 and 6. So we actually came to a very good conclusion, and we also analyzed the results in terms of average speed and the acceleration noise. Therefore, the proposed treatment in this phase 2 improved drivers' decision making when compared with the existing conditions. So the first hypothesis was confirmed, and you can see here the combination of signage and pavement markings that is proposed. And more than 80% of the participants of the online survey and driving simulator understood the bus and the no vehicle allowed symbols. That's why we use it. And the statistical evidence also supports the second hypothesis for variable average lane position, and also significant differences were obtained for the average speed and acceleration noise. Therefore, it is essential to maintain the uniformity in our traffic control devices that corresponds to the driver expectancy and how they understand what they can see. So in terms of recommendations, we also have here short-term, medium-term, and long-term recommendations to modify the existing signs to the proposed configuration that we were testing that was better, and incorporate also pavement markings and the combination of words and symbols. And in the long term, evaluate content measures with other features, maybe flashing beacons or other features that assist in reducing high-speed profiles. We also have some recommendations for future research using different types of signage in the short term and the long term to evaluate new extensions of the DTL or other designs or modifications. So we want to thank you for listening to our webinar, and we also want to thank the people who participated in the research, Brian Ruiz and Jonathan Ruiz, as we mentioned at the beginning, but also Ricardo Garcia and Enid Colon, who are currently graduate students and participated all along those research projects. And we acknowledge their contribution during this research. We also want to thank the Metropistas for providing the data that we use for operational analysis, and the Puerto Rico Highway and Transportation Authority for providing the as-built plans that were used as a base to develop our base scenarios. We want to thank our sponsors, of course, the UTC Safer Sim Center and the Metropistas, the UTC program, and the Civil Infrastructure Research Center of the University of Puerto Rico.
Thank you, Didier, and thank you, Ben. Yep, so
thank you
the chat box at the bottom right is open for any questions. I see Dawn is typing a question right now.
Thank you very much.
Thank you for the great presentation, though. It's very interesting and interesting work to see how some of these different interventions could help on that tollway. So Dawn is typing a question, and I'll read it once it's in. These different interventions could help on that tollway. So Dawn is typing a question, and I'll read it once it's in. So Dawn, she noted, thank you very much for the nice presentation. She found it surprising that drivers reported they did not understand the HOV icon. Do you have any thoughts on that?
Yes, well, some thoughts. I like Ben also to answer, but I believe that that particular sign is not very common or extensively used in all our cities. It is mainly used in the bus lanes in the San Juan metropolitan region, maybe, but it's not extensively used as in other places. So I think it's part of
She
the
also mentioned, did you find any other
environment.
items that they didn't
That's
understand?
exactly the answer. In Puerto Rico, that sign people seldom see it.
Not really. I mean, that was a big surprise for us, and I have to say that since we are now familiarized with these symbols and the MUTCD and also our students, it was natural for us to start looking at those symbols and try to use them because they are the norm, you know. So why not? But then the survey was the results were very enlightening, and I think that
Okay, we
we
have
should
another, or
take
Dawn is
care
typing
of that
something else, so I
in the
think she's
future
drilling you
results as
with
well.
questions. Uh, no, so she said if drivers don't understand signs, then mistakes will happen. So, yep, that's very important. Well, I'll give anyone a last, another minute to type in some questions. If not, um, I will send this recording. Or go ahead, Didier. Another minute to type in some questions. If not,
Let
I
me,
will send this recording.
uh,
Go ahead, Didier.
yeah, Jacob. Let me say also that it was particularly important here in this case in the DTL to have a very good signage and pavement markings because in one direction, in the eastbound direction, the exit for the vehicles to re-enter the freeway is in the right lane, is using the right lane. Meanwhile, in the westbound direction, they have to use the left lane in order to re-enter the freeway. And that is why it's very important to have a very good signage for them. Not everyone um, is a familiar driver, and for unfamiliar drivers, that may be definitely a problem. And also there is something that we found in the uh, using the cameras that the Metropistas um, has all over that particular dynamic toll lane. They have the camera, they can see when a driver takes the wrong exit, etc. And that happens more often than we would like to.
I want to make like a concluding remark associated with the presentation that I gave. That was a Jonathan study in terms of the posted speed limit. Uh, the the DTL, the dynamic toll lane, was posted 45 miles an hour. The main line lanes adjacent on both sides of the PR-22 are 55 miles an hour. And when the vehicles enter the DTL, and essentially they are like in a free flow condition on a straight tangent segment, they cannot perceive how they have to adjust to 45 miles an hour when they are essentially under a free flow condition, uh, unless they will see that the BRT was using the facility. Therefore, that was the reason that the vehicles were traveling at 55, 65, 60 miles an hour in the existing condition, not in the simulation. When we go to the simulation, the subject matters also perceive that they are on a tangent segment, that they can go at a faster speed. And that is very pertinent because we can see that both the subject drivers, as well as in the real scenarios, they perceive that they can go more than the 45 miles per hour posted speed limit. And we did a little bit of research of what was the original design, and it was based on the consideration of the child line, according to the actual roadside design guide, since those two lanes essentially don't have 10-foot shoulders, and they are essentially confined within the concrete barriers with barely 1 meter on one side, and there's a small pocket lane that is only 8 feet wide in a very short segment. The designer thought that having that obstruction of the concrete barrier was necessary to make an adjustment in the posted design speed. But our culture and the vehicles that are allowed inside, that are private vehicles, that are not necessarily heavy trucks, having many compact vehicles, private vehicles, and having close to having 11-foot lanes, and doesn't impede them to go at high speed. Therefore, that is the reason we are recommending to go ahead with the 60 miles an hour on the main DTL and 55 miles an hour on the DTL, because we also don't have a crash history that affects
I think that is everything. Thank you for that good explanation, Ben, and thank you, Didier, to both of you for the explanations and the presentation. It's very interesting work. So I think that will conclude our webinar today. We will have this recorded presentation online by the end of the week, and you can find that on our SaferSim website and our YouTube channel. And with that, I will like to thank you all for joining, and we'll hope to see you at our next one. Thank you, everyone.